We have defined the Gaussian distribution and its entropy in chapter 8. Basically, this entropy is differential entropy because it is a continuous distribution. And therefore, we are by far familiar with the continuous random variable, let's say Z, and its range is negative infinity to positive infinity, and this probability density function is Gaussian that we have seen last time. In this chapter, we aim to define the additive Gaussian chain. Okay, so we have defined Gaussian distribution and its entropy, and in order to use this knowledge in a channel relation, we define Gaussian channel. And this Gaussian channel is in fact additive Gaussian channel. What we mean by that is described by this equation here. So y is the received symbol. So y is the random variable for the output of the channel. Okay, its range is like this, and x is the input random variable, so input to the channel, and z is the additive noise added to the input x. And so this is a single channel use. So one symbol sent, one noise symbol added to it, and you receive it. So y is the received symbol, x is the transmitted symbol, z represents the noise added to the transmitted symbol x. So this binary operation, binary operator plus is the usual real valued addition operations. So for example, 1.5 plus 0.5 is 2.0. So that's the usual high school addition operation. Okay, so this type of channel is everywhere in our life. We'll see that soon. And in order to motivate this type of channel and how difficult it is to deal with this Gaussian, additive Gaussian noise channel, let us consider a very simple case. Suppose that at the transmitter we have two symbols selected, could be selectable, let's say plus 10, minus 10. So for in reality, this could be plus 10 volt or plus 10 ampere or minus 10 ampere or minus 10 volt. Let's just forget about the physical unit for these numbers. So here, plus 10, minus 10, we can select at the transmitter, and we send each one of these symbols, we send over a particular channel, and then when it this space between the two, the input output line, let's say here this space, this is the propagation medium. Okay, so transmission line or wireless medium, so such things. So you transmit with this much power or energy. By the time it reaches the receiver, in front of the receiver, okay, in the case of wireless communication, the energy of the signal sent has been reduced because it has, let's say, traveled a long distance, for example. So when it arrives to the receiver, just in front of the receiver, it is signal energy is +1 or -1. So these represent, you know, the energy reception or power reception at the receiver front end. And when it comes inside the circuitry of the receiver, basically there is a white noise added to the received signal. So it becomes, I mean, the received signal or received symbol. Let's say I call it Rx. The signal value has large spread. So basically, if it was received, +1 was received, then it actually comes inside the receiver circuit as a wide distribution of possible signal sample. Okay, so these are the spread, in order to represent how wide it can vary. Have a +1 here, and it could have large variance or large spread. And in terms of Shannon's language, Shannon described it as a fan. You're supposed to have this, but you have a fan of possible reception symbol like this. Okay, so just in terms of the picture, that's fan, size of the fan. And if -10 was sent, -1 is the energy in front of the receiver, receiver antenna, and then what's actually what is actually the sample, the value actually taken at the receiver circuitry because of the noise. Basically, noise occurs because of the electron movements. So there's always, additive white Gaussian noise. So you have a spread like this. So compared to the spread between the two, noise spread in this case is very large. So in this case, the signal to noise ratio is very small. Okay, so in this particular scenario, we have only two choices of a symbol that can be sent at the transmitter. We need to make out which one was sent at the transmitter. For example, positive symbol sent or negative symbol sent. We need to determine that. Then basically we have to draw a line, basically, and make a decision if the received symbol was a particular one. Let's say, for example, of this case, let's say, suppose that you received symbol value was somewhere around, let's say, right here. In this particular case, would you, what would you be the, what would be the symbol? I mean, what would be the decision that you make in this particular case? So it is lean toward the positive, side. So probably you said that plus symbol was sent. So +10 was sent. You could say, but there is a probability of error, which is because that -1 could have been sent, and then because it is within this fan, so this symbol is possible to be the sample value at the receiver circuitry. So in such a case, it is an error. So this region right here is a region of confusion. If you have received this one, you could clearly say, okay, because this is the outside of the confusion region, you could clearly say that this is positive simple sand. Or if you have received this, a symbol, around this here area, then you could say that, aha, this is, the -1 was sand. But here is where you have a large area of possible reception uh, that are in gray area. So in these areas, the probability of error occur. Okay. So can we make out in this particular case? So if this is the case, probability of error will be very large, right? Maybe close to 0.5, something like that, and close to 0.5, something like that. And can we make this error disappear? If it is possible, how can we do that? Okay, so that's the type of question that we need to ask. But here we were using only 2 symbols, but what happens if we use many symbols, many symbols? Then these fans, overlaps with each other like this, right? So it will be very difficult to make out, right? So the probability of error is very difficult to go away, right? So that's the usual layman's thought, right? So, but clever Shannon has designed this idea, came up with this idea of a channel code, and then he said, we need to use code in such a case. And as long as you choose your transmission rate per channel use is less than the capacity C, then you can make the probability of error goes down to 0, right? As n goes to infinity. What is n? The length of the code word. Okay. So that's the idea. So use a code and choose a rate of the code smaller than the C, smaller than or equal to smaller than the capacity. Okay. So that's the key idea. Okay. All right, that's the key idea. All right, let's erase some of them. Okay. So that's the motivation. A setup leading to motivation. So this type of additive noise is everywhere in transmission line, VLSI circuits, wireless medium, between the transmitter and receiver, between reader and the storage device, and so anywhere you have this problem of noise, which is additive to the signal. And this noise, tends to have, Gaussian distribution. Why? Because this noise is usually white noise. White noise is, there are large number of sources with different frequencies, with the energy of the noise source with a different frequency tend to have equal power, and in such a case, this Gaussian distribution has the maximum entropy, and in such a case, it is most difficult to deal with. And basically, if you have large number of independent random sources acting together, it tends to, it tends to have developed a Gaussian distribution. So for example, coin flip n times it is a binomial distribution, right? N coin tosses. P is the probability of head. But if we have large N, then this binomial distribution can be approximately described as a Gaussian distribution. So, binomial distribution converges in distribution to, Gaussian distribution with the mean NP and the variance NP times 1 minus P, or the number of emails in your mailbox per day. Have an average number of emails, lambda, but exact number is a random variable and is a Poisson distributed. But this Poisson distribution, when you have a large n, large lambda, then it also converges to Gaussian distribution. Why? Because there are the people who are sending you the email is acting independently with each other. So in such a case, this happens. So this independence random sources acting together in a large number, you tends to have a Gaussian distribution. So Gaussian distribution is very popular. When we have a channel described with a Gaussian channel, basically you have many applications. Okay, so one of the application basically, or example could be, conversation in a cocktail party. Everyone is talking loud, and what do you do in such a case? If you want to have your message conveyed to the other party that you are talking to, what do you need to do? One way is to scream very loud, right? That's a way of increasing the signal power, so that the counterparty who are listening to you, trying to listen to you closely, can pick up some signal so that they can understand. The other way is to use code. Basically, you can just have binary, symbols that you can say that, let's say R and O. You just have two symbol alphabet, and then use a code, binary code I and O to communicate with your party. And the other, noisy channel example is a deep space communications. So, for example, imagine that you want to communicate to Curiosity, which is sent to Mars to explore the Mars environment. So how do the Earth station communicate with the Curiosity? It has to travel large distance, so the signal attenuation is very large, So by the time the electromagnetic wave sent from the Earth station reaching to Curiosity antenna, the signal power is very small. And this this one, in order to make out the signal that you sent, or the message that you sent, then it has to be very smart. Okay, and the other case is worse. Let's say you have taken some picture of the Martian environment, and Curiosity wants to send the signal, the picture back to you, back to the Earth station. Okay, then it has to use the solar power generated, solar panel generated energy to transmit the symbols back to the, I mean, image back to the Earth station, but the transmission power, the signal power has to be very small, because this the energy at the curiosity is very dear, right? It is a limited resource, so it has a it has to rely on the battery power, so the signal power can be small, even at the transmitter antenna located at curiosity. And by the time it arrives to the Earth station, the signal power at the Earth station antenna will be very, very small. So it will be almost a negative SNR. Signal power is even smaller than the noise power. In such a case, in negative decibel SNR case, how can we do the communication? So that's the motivation for learning the channel coding theorem for Gaussian channels. So surprise! So even in this negative SNR scenario, use channel codes, and choose the transmission rate, which is smaller than C, the capacity of the channel. Then you can talk reliably to your partner over such a very noisy channel. So even over a negative dB SNR channel, where the signal power at the receiving party is significantly smaller than the noise power, you can still communicate reliably. So it is about overcoming this gray region, right? If your signal power is consistently smaller than the noise power, the gray region is going to be very huge. And how to overcome this gray region and make the probability of error very small, right? That's the surprise that the channel code idea has brought to us. Okay, so choose the rate small enough so that probability of error can be very small. So that means the capacity is going to be very small, and then you need to choose the transmission rate even smaller than the capacity, and you can find the channel code to convey your message or your image taken at the curiosity, sent back to Earth station with no error, okay, with zero error, almost a zero error, okay. Okay, so that's the motivation.